Hey, welcome. So, you know how we're used to organizing things in nice, simple lists, one thing after another, but what happens when your data just doesn't fit in a straight line? What if it's more like a family tree with connections that branch out all over the place? Well, today we're going to leave that simple list behind and dive into the powerful and really versatile world of data trees.
So over on the left, you've got the good old linked list. Just think of it like a train, right? Each car is connected to exactly one car behind it. It's simple, it's linear, totally predictable. But then look at the right. That's a tree. Now this is more like that family tree we were talking about, or maybe a company's org chart. One item, what we call a node, can branch out and connect to many others. And that single difference, going from just one connection to potentially many, that's what gives trees all their incredible power.
Okay, so we know it branches out, but what are the actual rules that make some branching thing an official data tree? Let's nail down a really clear definition.
At its heart, a tree is really just a collection of these connected nodes. And we actually use family-style language to talk about them, which is kind of helpful. A node that points to other nodes is called a parent, and the nodes it points to, those are its children. This whole parent-child relationship is absolutely fundamental to how trees work.
Now, a node in a tree can have a whole bunch of children, but one of the most common and, frankly, most useful types is the binary tree. And the rule here is super simple. A parent can have at most 2 children. We usually just call them the left child and the right child. Definitely keep this one in your back pocket, because we're going to come back to it in a bit to solve a problem.
And this is where things get really interesting. Say, not every structure that has branches gets to be called a tree. There are some really strict rules. And to get a good feel for them, let's play a quick game. I like to call it, Is This a Tree?
All right, first up to bat is our old friend, the linked list. I mean, it doesn't look very branchy, does it? So what do you think? Is this thing a tree?
And surprise, the answer is yes. A linked list is pretty much the simplest, most basic tree you can imagine. Remember that rule for a binary tree? A node can have at most 2 children? Well, here, each node has at most 1 child. It's a bit of a boring tree for sure, but it follows the rules perfectly.
Okay, let's check out this next one. See how the arrows are connected? We start at the top, we go down a level, and then, whoa, we loop right back up to where we were. So, is this a valid tree?
That is a hard no, and this gives us our first huge non-negotiable rule. A tree can never ever have a cycle. The connections always have to flow downwards or outwards from the top. You should never be able to follow a path and wind up back where you started.
Okay, last one for the game. Take a close look at this one. We have 2 different nodes up top, and they're both pointing down to the exact same child node. Does this structure make the cut?
And again, that's a no. This reveals our second critical rule. Just like with a real family tree, every child node can only have 1 parent. You can't have 2 different branches of the tree merging back together like this. All right, so let's just quickly recap the rules we figured out from our little game. A real tree has 1 special root node at the very top. That's the one with no parents. After that, every other node has to have exactly 1 parent. There can't be any loops or cycles. And finally, the whole thing has to be connected. You need to be able to trace a path from that root all the way to any other node.
Okay, so we've got the what down pat. Now let's talk about the why. How can we actually use this tree structure to solve a real problem in a really elegant way?
So here's our challenge. We're given a binary tree, and every node in it is holding a number. Our job is to write a function that calculates the sum of all the numbers in the entire tree.
For example, if we have this tree right here, our function should look at all the nodes, the 2, the 3, the 5, 6, and 4, add them all up, and give us back the right total, which is 20. The goal is simple enough, but how do we actually do it efficiently?
Well, the most elegant solution uses an idea called recursion. I know, it can sound intimidating, but it really breaks down into 2 super simple steps. First, you have the base case. If you ever reach an empty branch, a spot that doesn't exist, its sum is just 0. That's our stop sign. Then you have the recursive step. For any given node, the total sum of the tree below it is just its own value, plus the total sum of everything on its left side, plus the total sum of everything on its right side. That's it.
All that really means is that the time it takes to run the function is directly tied to n, the number of nodes. If you double the number of nodes, you basically double the time. You literally cannot get any more efficient than that. It is the best case scenario.
So the big idea here is that a really powerful, complex behavior, like summing up an entire tree,
can come from just a couple of simple repeating rules. And, this pattern isn't just in code, it's everywhere you look. Which kind of leaves us with a final question to chew on. What other complex structures, maybe in technology or even out in nature, are built from a few simple repeating rules? Thanks for digging into this with me.